don't think I gotta restart. I don't want to. There we go. Oh, where is the mouse? All right, let us roll. So today we are in 7.1, and we are estimating population means when sigma is known. All right, so the basic idea for this section is the basic idea for this section right here is there is a basic problem that we have in the real world that exists. Let's say, for example, I want to give everybody in this class, well, maybe everybody at the university, say, for example, a trinket or a token. Yes. It's kind of difficult. So let's say I say, hey, everybody's going to be happening at the amphitheater on Thursday, right? Since the tokens cost money, it doesn't make sense for me to say, hey, the university has 10,000 students. I need to buy 10,000 tokens, right? Most likely a small proportion of the university will actually show up. So maybe, 3,000 people will actually show up for the tokens, yes? And so it makes sense that I should just buy 3,000, yes? But the problem is that $3,000 is an estimate. Yes? In other words, what I'm trying to do is I'm trying to estimate the mean or the expected number of people who will show up for getting the free stuff. Yes? Of course, for example, if I say I'm going to give you pizza too, even more people will show up, right? Once you feed people, they show up. Yeah. Yeah. Right? And so the question right here is how can we form an estimate for that value mean, for that mean value right here? And so the way we do that right here is by first, excuse me, the way we do that right here, actually, let me just skip to that part right here. The way we do that right here is by first figuring out or estimating what the mean is. And then we put some boundaries on that mean. We can say, well, let's say expecting 6,700 people to show up, but at most, maybe 7,000 people will show up, and then at least maybe 5,700 people will show up. Yes? And so what happens right here, this gives me a relative bound on, okay, I know what number I expect, but I also know what numbers that maybe the high or maybe the low I can expect. Yes? And that can give me more confidence in knowing I have enough trinkets for everyone who shows up. Yes? And so what I'm doing is I'm shooting two birds at one stone. One, I am not overestimating. I'm not just going to buy 10 million trinkets to make sure everyone has one, right? But I'm also trying to prevent the case of not having enough. Yes? And so this right here is the idea that we're trying to do right here. And we do this through a process called creating a confidence interval. Questions there? So the basic idea right here is find the center and then try and figure out how wrong I might be or figure out how much error I might have. In this example right here, the error is 10 points. And so I'm going 10 points above and 10 points below to give me an interval in which the number of people who will show up will be somewhere between this interval with a high degree of confidence. Questions there? So obviously what we need to teach you right now is how to find the mean, and then how to find the error, how to find how much I'm off by on either side. Yeah, the first day after spring break is always the hardest because everyone is still in spring break mode. You know what I mean? So why am I here? You have to remember why you're here, guys. You remember why you're here. Oh, also remember, we only have 5 weeks, right? And so we are going to start the sprint to the end of the semester when all of a sudden your professors are going to give you all these assignments that they forgot about, right? And they're going to squeeze you, right? Yes. And so the sprint begins. And so it's very important right now that you stop, look at the semester as a whole, see what you've learned from how the semester progressed, and then use that to your advantage going forward, right? So you know you've been missing assignments for X, Y, and Z class. Make an adjustment to your schedule so you don't miss any more assignments, right? You know that this class has been your hardest class. Well, not this class, of course. Class X has been your hardest class so far this semester. Find that you have more time to study for that class so you can try and pull that grade up. Yes? Right? You've had the break. The stress is gone. Now is the time for you to finish off strong. Yes? I'm not talking to you. You guys all do great, right? Right. You guys all do great. In my class, anyways. All right. So the key thing again right here is we normally don't have access to all the measurements. And so what happens is we need to make a sample, right? What I might do right here is I might go back and say, well, you know what, how many people have went to the amphitheater last week, the week before, the week before that, the week before that? And that can kind of give me a sample, an estimate of how many people will show up if we say, hey, come to the amphitheater for X, Y, and Z purpose. Yes? But the fact is, I won't have access to every single day of or every single time a person has gone to the amphitheater, right here. And so then what we need to do is estimate mu. And then the key thing in this section right here will be under the assumption that the standard deviation for the population is known. The key thing right here is that the standard deviation of the population will be known if this is a process that's well organized and a process that has happened before. Yes, we've had elections many, many times. We kind of understand the standard deviation in the number of people who will show up on election day to participate, for example, right? We've had class attendance for years. We can figure out the estimate or the standard deviation for how many people will not attend class, right? These are ongoing processes. These are things that are going on forever. Unlike, for example, if I create a new model of a car, right? Let's say I've designed a totally new car. I gave it a new name, Flaming Bird or whatever. It's the first time we roll these cars off the line. I cannot really establish a standard deviation for the likelihood that a part in the car would break. Yes? Unlike say a F-150, we've been making these cars for years and years and years and years and years. We understand when and how they break. Question there. We will deal with this situation in the next chapter, 7.2, what to do when sigma is unknown. We'll deal with that in this next section. All right, so assumptions. The key thing right here about these assumptions is that these assumptions are exactly the same as in 6.4 and 6.5. Do you guys remember what happened in 6.4 and 6.5? Are you guys going to study that tonight for the test? Let me remind you then, the assumptions, right, are first things first, we have a simple random sample of size n, right? Remember there's an example with them cows, the heifers, and they had a sample of 125, I think it was, cows, right? They take a simple random sample of samples. Second, we need to have a sample size that is greater than 30. Remember this right here? 30 was the magic number. If you had a size of 30 or larger, then the CLT will hold the central limit theorem. Yes? Well, you'll read about it tonight. You'll read about it tonight. The central theorem will hold unless the underlying population is already normal, then any size population will hold. Yes? Maybe. All right. And so that was right here, our key assumptions right here. We're adding in that sigma is known right here. We're adding in that sigma is known as one of our assumptions. Questions there? All right. When we're in this situation right here, what we have to do right here is we have to do two things right here. We have to estimate the middle value, which is called the mean right here. And then this right here is also goes by the name of what's called a point estimate. A point estimate right here is a number that gives us a single value for a number that we like to know. In our example right here, we're trying to find the mean of the population. We will use the point estimate of the sample average to represent the mean. Questions there? So in other words, if I'm looking at the people in my amphitheater, right? If I look for the last 5 sessions, 3,000 people showed up, 2,500 people show up, 3,200 people showed up, and so forth and so on. If I simply take the average of that group right here, that average will be a good estimate for the that average will be a good estimate for the actual population mean. Okay? So what we say right here is that the sample mean is an unbiased estimator of the true mean. Okay? So for example, if I wanted to know what was the average for my class on test number 2, I don't have the entire class right here, yes? But if I take you guys' average score, that score will be really, really close to the actual class score. Okay, means are unbiased. Means do a good job of estimating means themselves. Questions there? That is because a normal distribution right here, what's at the center of a normal distribution? The mean, yes? If I take another sample from that sample, the mean will stay the same, right? And so because of that right here, the sample mean is a good estimate for the population mean. Questions there? Again, the sample mean will never be exactly the population mean, but it is a good estimate for the population mean. Questions there? Because it's a single value, we call it a point estimate. Questions there? But because we know that the sample mean is not exactly the mean, we have to have something called the margin of error. The margin of error is the difference between the point estimate and the actual mean. And what we have to show you is how to calculate or to estimate the margin of error. Questions there on the key terms, point estimate or margin of error? All right. Your margin of error, mathematically speaking, is simply the sample mean minus the mean for the entire sample or the population mean. And this can be written in this way right here to get rid of any negative signs, the absolute value. Oh, sorry. Since the mean is usually not known, otherwise we would just use it, right? We have to find a way to figure out how close x is to the mean right here. And thus, in other words, we need to find a way to calculate the error. This is not what I wanted to next. Give me 1 second. Let me just do it in order. I'll come back to it in a second. All right, so a random sample of 100 fourth graders is selected to take part in a new experimental approach to teach reading. At the end of the program, the students are given a standardized reading test. On the basis of past results, it is known that the scores on the test will have a standard deviation of 15 points. So what I know is that out of 100 students, I got an average score of 67.3. And the administrators want to estimate what the mean score would be if the entire population of fourth graders had enrolled in the program. All right, so let's break this down a little bit. We have a current way of teaching reading. Yes, everyone, we're not getting 100%, so we want to better the situation. Yes, and so what they did was they created a new approach to teach students reading, right? But do you just simply go and take that approach and they say, hey, we're doing this now? No, we got to go through some kind of testing process to try and figure out if this reading process is as good as it claims to be. Yes? And so what they decided to do was to put only 100 students through this process. Make sense? All right? The 100 students did it right here, and then this was the average score for those 100 students. Question, if the school district had 10,000 students, if all 10,000 students took the same process, do you think the average would be exactly 67.30? No, it would not, right? So the question is, how far off are we? And that right here is what the administrators want to estimate. Questions there? Because let's say in the old reading system, students would score an average of say 60 points, right? Does this 67.3 mean that students overall will do better? We're not 100% sure because we know that this is not the exact mean. Yes? Let's say the exact mean was actually 60 points. This is just a little higher. Maybe they chose from a school with more affluent parents or whatever. And so the score ends up being higher because of the choice of students. Then the system isn't actually better, is it? Right? And so what they need to do is to find a way to put bounds on this number, to put an estimate on this number. Questions there? Okay. And so what they need right here is first to establish a point estimate. Your point estimate is going to be 67.3. This is normally the top line number that they will report. And so, for example, they will say 67% of students scored 67% on this new test, right? That's the top line number. But the professionals will then look for a second number. And that second number right here would be what we will call the error or the margin of error. In this example, our margin of error is 10 points. Then that means we can either be 10 points low or 10 points high. And so in other words, we'll add 10 points right here and we'll subtract 10 points right here. And what that would tell us, is that our margin of error, and what that would tell us is that our margin of error, also our true mean, is between these two values. Questions there? You guys okay? You guys need a high five, a hearty handshake, a positive word? You can do it. You guys expend a lot of energy during spring break, huh? Because normally, even on Mondays, normally you guys have more energy than this. You know, I have my theory. You guys use up all your energy in the weekends, and then Monday just making it here. Then by Wednesday you're okay, and then Friday waiting for the weekend. No, maybe. Excuse me. And so again, the key thing right here is that the average score was 67, but what we're saying is that the true mean is somewhere between 57 and 77. All right? We're saying we do not know the exact value for the true mean, but we expect that it's between these two numbers. All right? And so, for example, let's say the old reading scores, the average score was 50. Right? Let's say the old reading score, the average score was 50. We know, therefore, for a fact that this reading system is better. Because even if the mean was only 57, that's still higher than the old reading score, yes? Yes? And so we can use this right here to make a concrete decision. And that decision right here is this method right here is better. Does that make sense? Does that make sense? The old reading score was 50. We want to know if the new system is better. I cannot simply look at the 67 average and say, oh, it's better because it scored a 67. The true mean is not this number, right? The true mean is not this number. If I can establish a boundary, how far I am off, in this case right here by 10 points, I can give you a lower and an upper bound on the true mean. The true mean is between these two values. I can then make a decision, say, well, the old score was 50. The new mean after the new teaching process is between here and here. Clearly, this new system is better. Questions there? This is also stating that the mean score could be as high as 77, right? Again, this average is just low. This is also saying that the true mean can be low as 57.3. Again, this means this average is just high, right? But the fact is the true mean lies somewhere between these two values. Questions there? And in this case right here, since the current scores for students are 50 points, it makes sense to put in the new system. Questions there? All right, so the key thing right here is the plus or minus is called the margin of error. And what we have to do is to teach you how to calculate the margin of error. We don't just randomly pick a number from the sky and say, I feel like the margin of error is 10. We don't randomly just pick a number. We go through a statistical process to calculate this plus or minus. Questions there? All right. All right, and so to go over this again, the first thing we do is we establish what's called a point estimate. It is the average. It is our best guess as what the actual mean is. But because we know that it is wrong, we found two boundary values, a lower boundary value, a lower confidence interval value, and a upper boundary value. This are always the same distance away from the mean. In this example, 10 points right here. And these two numbers together are called a confidence interval, or a CI. Confidence interval. We can use confidence intervals to estimate the true mean, mu, for a population. You can use a confidence interval to estimate the true mean for an interval. The mean, mu, lies between these two values. We don't know the exact value. The only way to get the exact value is to do the entire population, yes? Right? Give every single person the reading system, have them take the test, and then find the average for all the scores. That's the only way to find the true mean. This right here is the way of estimating the mean right here. Questions? Cool. All right, so we have to go through some concepts right here. We have to go through what's called a confidence level. We have to go through what's called a standard error. And then we have to go through what's called your Z-score, your critical level. And so we need to go through each of these one at a time. I got time. All right, so based on the sample of 100 fourth graders, using the new approach for teaching reading, we shall construct a 95% confidence interval for the mean score. First and foremost, what does this mean? A 95% confidence means that the boundaries we give, the upper and the lower value, we're 95% sure that the true mean is inside that value. If I had a 99% confidence interval, two boundaries, then we are 99% sure that the true mean is inside those two values. Does that make sense? I am saying I have high confidence that I have captured the true mean, right? So if I say the average for the students was between, say, 62 and 64 with a 99% confidence interval, I am telling you that basically the mean is inside that value. I'm 99% confident. For elections, when they are running election, they make a call for the election. Almost all the time when they're making a call for an election, they are 99.99% sure that the call that they're making is correct. So in other words, only about 1 in 1,000, only about 1 in 1,000 times they make a call, the call will be incorrect. Okay, that's what they do. They make a confidence interval for the scores that they're seeing. This person has 40% of the vote. This person has 60% of the vote, and then they're making a confidence interval as to whether or not one should be replaced, should be higher than the other. And they only make a call for an election once they're 99.99% sure that the two numbers you see are as it is. Questions there? All right, so like I was saying right here, if I have a 95% confidence interval, it means I am 95% confident that the true population mean falls within our interval. In other words, there is a 5% chance that the true mean falls outside of our interval? Question there. All right. This right here is a picture that's meant to show you this in real life. Let me show you right here. So you see at the bottom right here, this right here is the mean. Yes. And what happens right here is that you can see right there are about 100 lines. And so basically what happens was they took an average 100 times. So let's say how many school districts do you think they have in the country? I think they have like what, maybe 20,000 school districts in the country. And so what happens is they went through 100 of them, and they taught those 100 of them the new reading process. Yes. And what happens right here, that came up with a confidence interval. Yes. Each class would have a different mean, right? Because this class might have gotten 67, this class might have gotten an average of 72, this class might have gotten an average of 55. Yes. If I construct a confidence interval for each one of these, this is what each bar represents. See this bar right here? This represents a confidence interval. They're saying I am 95% sure that the true mean is between here and here. Okay? And in fact, you can see it is. You can see this line right here. This line represents the mean. You can see that the mean is inside this confidence interval. Yes? But if I am 95% sure that the true mean is inside the interval, then that means I am 5% sure that the true mean is not inside the interval, yes? And so if you look very carefully, you will see about 5% of the time, they will form a confidence interval that doesn't capture the mean. See this one right here? It didn't capture the mean. See, there's another one right here. It didn't capture the mean. There's another one right here that didn't, but only 5% of them, right? And so in other words, I'm trying to say, hey, I'm really confident, but I'm not 100%, I can't guarantee, yes? But I'm saying right here is that if you give me these two numbers, most likely the mean is going to be inside that interval. Questions there? Notice that we're not guaranteeing that the mean is at the center of the interval, right? We're not guaranteeing that the mean is at the center of the interval. We're just saying the mean is inside of the interval. Questions there? One of the issues we have with statistics is we can't guarantee anything, right? Even though I tell you this team has a 95% chance of winning, I think the Gators, number one, they were playing number Iowa last night. I'm pretty sure they had like a 80, 70, 80% chance of winning, and they didn't, right? The problem with statistics is even if I can give you a number, I can't guarantee the outcome, the nature of random events. Yes? Yeah. But if those same two teams had played 10 times, most likely the Gators would won the vast majority of those. Yes? But this one time, they did not. Questions? Excuse me. So again, if we draw samples right here from 100 different institutions around the country, and we form 95% confidence intervals, 95% of the time, the interval will contain the true mean. And remember, the true mean is if every single student across the entire country took the process, took the exam, and we took the average for the exam, that's the true mean. Yes? Questions there? All right, so that takes us into creating a confidence interval. Your confidence interval is simply the mean x bar plus or minus a value e, and that value e is called the margin of error. The value e is called the margin of error. The way we calculate the value of e is by multiplying two numbers together. The first we call it z star, or the critical value, and the second we call the standard error. Do you guys remember seeing the standard error before? Remember seeing the standard error before? If you recall, from chapter 6.4 and 6.5, we do not use the standard deviation, yes? We take the standard deviation and we divide it by the square root of the sample size, yes? Right? Remember, I showed you guys the whole picture right here, and that if you're taking a sample, the standard deviation always gets smaller, the mean stays the same, but the standard deviation always gets smaller, yes? 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 Oh, you guys got some studying to do. All right, all right. I believe in y'all, though. I still believe in y'all. Right? The standard error is the value we use for the standard deviation in this process. All right? Question there. In other words, the larger the sample size, the smaller the error is going to be. I am dividing, yes? The larger the sample size, the smaller the standard error, the smaller the error is going to be in our calculation. Questions there? All right, so let's go through each of these pieces tomorrow. All right, yeah, I don't want to get too far because we have the test coming up in chapter 6 right here. I just want to first just remind you of some key facts on the test. The first right here is the empirical rule. If you are one standard deviation from the mean, what percentage of data are we capturing? 68%. If we're two standard deviations away, how much percentage are we capturing? And if we are three standard deviations away, how much we're capturing? Almost all, 99.7, right? This will not be given to you on the test, so you do need to learn and memorize these numbers, yes? If you forget, you can use SALT to give you an estimate, yes? You use SALT right here, you're putting Z as 0, mean as 0, and standard deviation as 1. If you put what's the probability between -1 and 1, that will give you one standard deviation off, yes? And the answer will be 0.68349, I think. But that's basically 68%. Yes? So if you forget these numbers, you can at least get an estimate from SALT, right? Remember, if the question says use the empirical rule, do not use SALT because SALT's answers will be too accurate. Yes? Use 68%, 0.68. That's it. All right, so that's the first thing I want to remind you about the empirical rule. The next thing that I wanted to remind you guys about right here is your z-scores. You guys remember what a z-score is? If you are told that this is a z-score or a standard score, it means the mean equals 0 and the standard deviation equals 1. Yes? They will not tell you the mean and standard deviation. They will just tell you it's a standard score, it's a z-score. You must then remember those two values. All right? Questions there? They will then ask you, for example, what's the probability of being to the left of a certain z-score or being to the right of a certain z-score or being in between? Those are just the buttons you need to click on SALT. Yes? If it's less than or to the left, you click a left tail test. If it's greater than or to the right, you click a right tail test. If it's in between, you click on in between in SALT. Yes? Yes? Then SALT will give you the probability, and that's going to be your answer. Questions there? So we won't be doing all of these table stuff right here. So example, find the area to the left of 1.26. You just go ahead and click a left tail test, putting mean 0 and standard deviation 1, and then SALT will give you that probability. Questions there? You also have your inverse problems. Your inverse problems right here is when they give you the probability and then they ask you to find the corresponding z-score. Where is my inverse problems? I lost them. Yeah, that's all right. They ask you to find the inverse probabilities. So what'll happen is they'll tell you it's a left tail test. They'll tell you the probability and then ask you for the z-score, right? Remember, for salt, you just put the probability in, and then the z-score automatically fix itself on top. Yes? Questions there? And then, of course, you have, when it's area under any curve, in these situations, the mean and the standard deviation are not 0 and 1. The mean in this example is 272, and the standard deviation is 9, and those are the two numbers you plug into salt. And then left tail test, right tail test in between to give you your probability. Questions there? The inverse works exactly the same way. So if I pull up salt, by now you guys should have this memorized on your fancy tool right here. Again, you should select normal distribution. Remember last time we did binomial distribution, yes? We're going to be doing a normal distribution. 7.2 will be the t distribution. That's going to be the next distribution we do. Now, distribution right here, mean 0, standard deviation 1. This means this is a standard distribution, yeah? Standard normal distribution, okay? And then if I have over here a left tail, and I put in a score, for example, of 1.26, 1.26, like so, this is the probability that you're less than 1.26, 89.617. If you click on between right here, and if I want to know if I am within one standard deviation of the mean, put a -1 right here and a +1 right here, we get an answer as approximately 68%, as we expect. Questions there? Again, notice that this is more accurate than the 68% from the empirical rule. If, on the other hand, I want to know what's the z-score if I have 72% shaded to the left of that z-value, I put in 72 right here, 72%, and then it will give me my score above it right here. This is the inverse norm. I plugged in the probability, and then it gives me my z-score up here. Questions there? Of course, in the real world, everything is not a mean of 0 and a standard deviation of 1. I think for the what was it? There was a mean of 272 and a standard deviation of, was it 9 days? I can't remember. But it doesn't really matter. You have those two numbers in right here. And then what's the probability that's we're less than 250? You just put in a left tail test. Notice there's the less than right here. And you let's plug in 250. It's going to be really small, isn't it? Yep. And the probability that you score less than 250 is this right here, less than 1%. All right. Let's say I was told that the probability is 80%, 0.8. That means the person scored less than 280, my round. Questions there on using salt? Remember that salt gives you the z-score breakdown right here. So you see the mean is in the center, 272. If I go up 1 standard deviation, that's going to be 281. If I go up 2 standard deviations, it's going to be 290. Remember, we did that process where it just added in the standard deviations each time? Yes? And then subtracting them, going the other way, 1 standard deviation down, 2 standard deviations down, 3 standard deviations down, and so forth and so on when we were doing the empirical rule problems. Questions? And of course, the one problem I have with all of this lovely knowledge that we have is that this knowledge can fail us and this knowledge can trick us. Yes? If we are in section 6.4 or section 6.5, there is an error. So 6.4, 6.5. When we are looking at sampling distributions, instead of looking at a single value, we're looking at a group of people. Right? And whenever we're in a sampling distribution, the standard deviation is not the standard deviation. Yes? Yes? So first things first, I mentioned this a little bit earlier on, but it is the central limit theorem. That's what we use right here. N has to be larger than 30 unless the underlying distribution is normal, and then any size will do. N needs to be one or more, right? But the key thing right here is, where is it? Where is it? The key thing right here is the standard deviation for the sample is not 9.5, right? Based on data from US Census, the mean age for college students is 25 with a standard deviation of 9.5. When I'm plugging this into SALT, I do not use 9.5 as my standard deviation. Yes? Because we're looking at a group, in this example, a group of 125 students, the distribution of the average was going to have that the standard deviation is going to be the standard error instead. Remember we just saw the standard error? Sigma divided by the square root of n. Yes? And this is the most common mistake on this test. They just plug in the 9.5 because, hey, it says sigma equals 9.5. Questions there? So I got to work this first out. This works out to be 125 square rooted is 12 squared is 144. So this works out to be about 11.01. So 9.5 divided by 11.01 is approximately 0.82, somewhere around there. And so it means I'm going to plug in 0.82 for the standard deviation. Questions there? Comments, queries, concerns. That's the main difference. Of course, when preparing for this test, I got to remind you, by definition, an unusual event is one where the probability is less than 5%. Other than that, the key thing to remember is that all the questions come from WebAssign. And so if you do well on your WebAssign homework, you should do okay on the test, as you hopefully have noticed so far. Yes? The time when you were flustered and you didn't have time to finish your homework, or you got several questions wrong on the homework and you never had a chance to go back and fix them. Those are the questions that showed up on the test. Yes? And so please ensure that you can solve all of the problems on your homework. All right, any questions before I send you guys on your way? All right.